A look at domains. A domain is a set of rules that define permitted values for an attribute. They constrain data values and ensure data integrity. A domain is defined in GeoDatabase as a unique entity. If a feature class has been subdivided using a subtype, then different domains can be applied to each subtype. There are two types of domains, coded domain and range domain. Coded domains are a list of valid values. Range domains are a single permitted range of numeric values. With FME, you can write to an existing table using an existing domain, or write to a new table using an existing domain, or write to a new table creating a new domain. These options are controlled by the data type parameter and the valid features to write parameter. Details about these three different scenarios can be found on pages 24, 25, and 26. Keep in mind that you cannot write to an existing table while creating a new domain or creating an association with an existing domain. Also, you cannot create the domain dynamically as part of the workspace process. It must be manually defined prior to execution. Let's take a look at writing a coded domain in example 4 on page 27. So in this example, we're going to load some water distribution data into a feature data set. We have a source file that contains a number of different layers, one of which has an attribute which is suitable for validation using a domain table. Okay, so we're going to start up Workbench. We never did save our previous example. Let's quickly do that. Example 3. Always a good idea to save your workspaces. Now, for this particular example, we have a pre-existing workspace, the Esri 4 Begin workspace. I'm going to go to Open Workspace. And that is being kept in C, FME Data, Workspaces, Pathways Manual. And it is the Esri Example 4 Begin workspace. So this is my existing workspace. Let me just full screen this for a moment. Whenever you're confronted with a new workspace, do a quick look over it for basically legibility. In this case, you'll notice that the names of the various feature classes are too long for them to fit in the feature type title. Quick and easy way to get around that. If I just select all of those destination feature types and right-click on them, I can attach annotation. The annotation default value is the name of a feature type, so we can see the full names here. Makes it a lot easier to spot our water distribution lines. Likewise, I can do that for the source. I'll select all the source feature types, right-click, and attach annotations. So we're reading in 2 feature types, but writing out 3. This is because the source has 2 possible geometries in the source layer, and in the outputs, you're only allowed a single geometry type. Also, if we go into a destination feature type definition, under Format Attributes, we'll notice that there's a feature data set, which will contain all 3 of these feature classes. Also on the sources, we're exposing a number of format attributes like AutoCAD block name. That's so we can store this information in the geodatabase. Now, for this particular translation, what we're really interested in is the water distribution lines. And we want to use a coded domain for the diameter attribute. So in our output feature type definition for the water distribution lines feature class, we can double click on that and take a look at the user attributes. Currently, diameter is set as a type double. Instead of using that, we want to use a coded domain. So we'll double click on the type and choose coded domain. When we click on edit, we can create the domain name, or the coded domain of diameter. We want to create that. It is going to be of type double. And now, unfortunately, I have to do a bit of typing. And unfortunately, you have to watch. Sorry. Inches, 2 to 2 inches, 2.25 to 2.25. 4 inches, 6 to 6 inches, and 8 to 8 inches. So hit OK. We can save this workspace. Let me just make sure that I'm not currently viewing that geodatabase. Refresh that. And then I can run the translation. Now there's some questions that came in. Can you export domain or domain values within a geodatabase to a diagram? No, we can't currently do that. And can you import domain values instead of having to create them manually? And no, ultimately we do recommend creating the domain values within our catalog. So let's take a look at what we have here. Resources, Esri, geodatabase. If I go into the properties here, I can see that it created under domains. Oops, I have to do a refresh here. Annotation status. Odd. May have to come back to that later on. Let's see, did I miss something here? Well, I have to come back to that a little bit later on. Usually the domain shows up in here. Under the properties, I find the domain here. But for some reason I'm not seeing it at the moment. I'll try to circle back around to that later on. But that's basically how you write out to a domain. Let's move on to subtypes. Subtypes are subsets of features within a feature class. It is an alternative to having multiple feature classes for each type of feature. For example, you can have a feature class of roads and then subtypes based on their condition: good, moderate, and bad. Subtypes only apply to a single feature class, so you cannot create a new feature class and associate an existing subtype to it. So your options are write to an existing table with an existing subtype, or write to a new table and create a new subtype. Details about these scenarios can be found on page 30 and 31. When creating subtypes, you can use one of two data types: subtype codes and subtype. Subtype codes allows you to define a codes number and description. Subtype just allows you to define the codes. Let's take a look at using subtypes in example 5 on page 32. So in this particular example, we're going to load the parks data into a geodatabase. And parks will be assigned a different subtype to signify whether they are small, medium, or large. So I'll save our workspace here. I'll generate a new workspace. Let's specify our source data set. We want to bring in our data parks. And again, we're going to write out to our city data geodatabase. Okay. There was a question here, can you apply a domain to a subtype? And I believe yes, you can. If you have multiple subtypes, you can apply a domain to each one. Now in this particular workspace here, sometimes when you create a workbench workspace, you'll find that geometry filters have been brought in. This happens when FME is not sure if there's multiple geometry types in your source data set or your source feature type, and you are writing out to a format that only allows a single geometry type per feature type. In this case, we have, if we examine our source data, you can always right-click on a source feature type and choose Inspect. This is the same as right-clicking on its reader and choosing Inspect. We can inspect our city parks and see that they are, in fact, polygons. So all we really care about is what's coming out as the polygons. Everything else can be deleted. So I'm going to delete all my other feature type definitions. Connect this up. Always a good idea to double check your feature type definitions. In this case, I don't want to call the output feature class City Parks Polygons. I just want it to be City Parks. And just confirm that it's writing out to a polygon. For this particular translation, we're going to want to calculate the area. So I'm going to add an area calculator. That'll calculate the areas, and then I want to provide a new attribute value depending on its area range. For that, we have a range mapper, specifically an attribute range mapper transformer. Within the attribute value mapper, or sorry, attribute range mapper, my source attribute is going to be area. The output is going to be park size. Going from nothing to 25 or 250,000, that will be 1. That's basically the output code. From 250,000 to 1 million. Maybe code 2, and from 1 million to no upper limit, that'll be code 3. Notice we have duplicate values here. The feature will be given the value of the first one that it matches. So if something is exactly 250,000, it'll be given a value of 1. Okay, now similar to setting the domain, we can set the subtypes by going to the user attributes. We'll add a new attribute called park size. And its type is going to be subtype codes. There we are. And again, we can edit this for our subtype codes. Code 1 is a small park. Code 2 is a medium park. We can put spaces in there. And code 3 will be a large park. Again, let's just make sure I'm not viewing that particular data set. And let's try writing out to that. Actually, always a good idea to save your workspace as soon as you get some stuff into it. Example 5. Let's run this. Okay. Now I should have my city parks. There we are. Drag and drop that in. Here's my city parks, and you can see they all have different colors based on whether or not it's a large park, medium park, or small park. And when we query a feature, we can see that the park size, instead of giving us 1, 2, or 3, is being mapped to large park, medium park, or small park. Now moving on to geometric networks. Geometric networks store topological relationships between line and point feature classes in a feature dataset. They enforce data integrity and connectivity between features. FME cannot create geometric networks or the feature classes using them. Both should be created before the translation by using ArcGIS. FME can load data into existing network feature classes, or create simple point and line feature classes, which then have their geometric network created as a post-processing step. When reading geometric networks, FME creates a number of format attributes, such as GeoDB element ID, GeoDB from junction element ID, and GeoDB to junction element ID. Reading is faster if the network information is ignored. There is an ignore network info parameter for the geodatabase reader. On to relationship classes. Relationship classes manage the relationships between features in one class with features in another. When reading a relationship class, both the origin and destination feature classes must be read at the same time as the relationship class. Relationship classes cannot be created by FME. They must be set up using ArcGIS before running the translation. When writing relationship classes, the allowed geometries must be set to either GeoDB relationship or GeoDB attributed relationship. Both attributed and non-attributed relationships can be read and written with FME. There are also some format attributes that must be set for all features being written, namely GeoDB rel origin OID, GeoDB rel destination OID, and GeoDB type. Also, GeoDB OID and GeoDB feature has relationships must be stored on features being written to the origin and destination feature classes. The GeoDB OID or object ID values are not actually written to the geodatabase. They are only used by the geodatabase writer to tell which features are in fact related. Be careful if you have more than one geodatabase writer in your workspace. Also, note that attributed relationships can be inserted, updated, and deleted, but non-attributed relationships can only be inserted and deleted. We're going to skip example 6 on page 40 and move on to the attachments on page 46. Example 6 uses a spatial relationship, while example 7 uses an attribute relationship. They're very similar in concept, so for sake of time, we're going to skip this example. Example 7 uses attachments. Attachments allow you to connect additional information to features as a file or multiple files. This is a form of relationship class, and is done by reading in the contents of the file to be attached as an attribute, and writing that attribute to a data field in the attachments table. Let's take a look at how this is done in example 7 on page 47. So in our catalog, I'm just going to navigate away from that. And let's get back to Workbench. Okay, so for this particular example, the city has a database of emergency facilities, and they want to add in photographic images of those facilities as attachments in the geodatabase. So let's go back to catalog here, just take a look at what we currently have. As we mentioned, the definitions for all these have to be already existing in your geodatabase, and you can see them here. We have our emergency facilities and the attachments for the emergency facilities. And we're going to want to populate those tables. Now, I don't know if there's an easier way to unlock that geodatabase as opposed to navigating away and refreshing. If you happen to know of one, let me know. So let's start up an existing workspace. I'm going to go to Open. It's being kept in C, FME data, resources, Esri, oops, sorry, no, wrong location. FME data workspaces, pathways manual, and it's Esri example 7 begin. Oh, this option used to work. Okay. So I'm zoomed out a little bit here. Doesn't look quite nice. So I'm just going to go to zoom, zoom into 100%. It brings us in a little bit closer. That might be a good idea to bring in an overview window. Once your workspaces get large, having this overview window down here can be quite helpful so you can look around the workspace. To help us along with this particular example, we have the transformers that we need to use along the bottom. So the first thing that we're going to want to do is adjust the writer type. We're going to change that to transactions. Or sorry, change that to edit sessions. Next up, we're going to want to create some attributes. Namely, we want to be setting the GeoDB feature has relationships. That'll tell the writer that what the features being written out have a relationship. And for that, we're going to use this attribute creator here. Just going to bring this up. We want to use this for both sets of features coming in. This one contains the path to the photos. Basically, it'll be reading in those photos. And then this one up here contains the actual 911 facilities. We want to tell that those features have the relationships as well. So I'm just going to duplicate this transformer and bring that in here as well. So this is basically just creating GeoDB feature has relationships and setting that to yes. Now each feature will have to have a unique ID on it for use later on. It's how we're going to relate them to each other, and it will be used by the writer. If we look at our source here, it doesn't have any unique ID already existing for our path, and I believe the E911, well, it's got a whole pile of IDs, but we can't really be sure of which of those is actually a unique ID. So we're going to create our own unique IDs by using a counter. So the counter just counts each feature and gives it a count value. So I'll bring that in here and duplicate that for the other one as well. So in the counter, we have two separate counter transformers, but they're sharing a single counter name. That means that each feature will have a unique GeoDB OID value. Because as the first feature comes in here, it'll be given a value of 1. If the second feature comes in through here, it's not given a value of 1, it'll be given a value of 2. Okay, so we'll connect our output GeoDB OID to our destination. And for our files, we're going to connect that into these ones here. These are setting up various attributes. So we're copying the values to object ID, or rel object ID, ATT name, data size, content type, etc. Setting the content type. And then we're taking that file and loading it into the data attribute. So what we've done so far, we'll load up the attachments table and the emergency facilities feature class, but now we have to relate them to each other. We're missing one more thing from here. If we loaded this data, this E911 data, directly in, right now it's just an Excel spreadsheet, or what is it? MDB. No, it's an Access database. It doesn't have any geometry yet, so we'll want to create some geometry. We can bring in our 2D point replacer. That's down here at the bottom. So we have a 2D point replacer. Let's bring this up and drop that in. There we go. So now we've got some geometry. Okay. Now to create some additional format attributes, we want to copy our GeoDB OID into GeoDB rel origin OID and GeoDB rel destination OID. So I'm just going to duplicate this. Our E911 data is our origin. So we have GeoDB rel. So all work better if I spell it right. Origin OID. And I need to set this to GeoDB rel destination OID. And now we want to merge those together. So our facility locations will request the object IDs from the imagery. And in the feature merger, we match them together, name full, path route name. So basically matching the images to the name of the facility. We remove any unwanted attributes and then write that out to the table. Okay. Now we still have to set the type of feature that is. So let's copy this in here. Now if you're removing attributes, let's just add this to it. There we go. So we're setting our GeoDB type, and we want to set this to GeoDB relationship. So tell the writer what type of feature this is. Oops, geo B. Relationship. Okay, if I got all that right, we'll run the translation. Oops, did I forget to navigate away from it? Nope, looks like we're good. So that ran in there. Let's see what we have. So I have my emergency facilities. I'll drag and drop those in. And if I did this all right, hold on. Created the geometry. That's right. Just remove everything here. And there we go. So I can choose my emergency facilities. I think the source I had was just in a different coordinate system. So they weren't in the same location as the parks which I already had. So here's my various facilities. I'm going to use the HTML inspector. I can see pictures of those facilities. Okay, moving on to the database transformers. In the database category in the transformers gallery, show that quickly here in Workbench, we have our transformer gallery, and in this we have a database category. There are a number of transformers that can be used to interact with databases. That's useful to us because geodatabase, well, it's a database. Sometimes it's useful to use a transformer because you only want to work on a smaller subset of your data, or use some special clause. When using the database transformers, one SQL or other database command is issued for each feature entering the transformer. Some useful database transformers are the SQL executor and SQL creator, which is very similar to it. Also, there's the ArcSDE querier and the feature reader. The SQL executor and SQL creator can execute any arbitrary SQL against any of the database formats FME supports. I've used this to essentially create a view from multiple Oracle tables. The ArcSDE querier can update, insert, or delete features in an ArcSDE database based on what attribute values are on the feature entering the transformer. I've used that transformer in previous projects. A feature would come in, I'd query a grid area from that, and then use that to delete all the existing features in that grid, so then I can reload the data. We'll be taking a look at the feature reader in example 8 on page 53. But basically the feature reader allows you to read in from a database just the features that you're interested in. Okay, so example 8 in Workbench. The task here is to read in all the addresses within a specific city grid. Because the addresses do not have a city grid cross-reference, we'll have to do this spatially, basically query a file-based geodatabase or file geodatabase to find the addresses within a grid area. So one method would be to read in all of the addresses and all of the grids and then match them up. If you have a huge amount of data, that could invoke a fairly serious performance penalty. So instead, we're just going to query based on a spatial area. So I'm just going to save my previous workspace. Now we're going to start with a blank workspace. Okay, I'm going to add in a reader. It's our file geodatabase. I'm only interested in one table. I only want the city grid. Now, for selecting the city grid, there's two ways that we could go about this. With this particular geodatabase reader, there is a where clause. We could concatenate some parameters together to populate that where clause. And that would work, but that's a little bit complicated. If you're actually doing this in practice and you had a large amount of grids, that might be something to look into. You could look into concatenated concatenated user parameters. We're going to do it in a bit of a simpler way, which with the small number of city grids that we have, there's not a noticeable performance hit. So this is the easier way to do it. What I'm going to do is still use a published parameter, or user parameter. Give you a choice, the name of this parameter, grid square. It is published. It is not optional. You have to choose one. Select grid square to filter by. And then we have to enter in the possible grid squares. Now there's a lot of them in our grid, city grid. To make life easier, we can import them. So I'm going to bring those in from my city grid. It is my, let's see, tile name. It found 30 unique tile names and imported them all in. So that cuts down on a fair bit of typing. So now I actually want to make use of that grid. And for that, I'm going to use a tester transformer. So this is the quick and easy way to make use of that. So wherever tile name equals, and if I double click on it, choose the drop down, I can choose that published parameter, that user parameter which I just created, grid square. So whenever the tile name equals the grid square that I've selected, that'll pass the test. Okay. So it's a good idea to actually test to make sure that's working. Step number 5 here. I'm going to right click on my tester and connect inspectors. That'll connect inspectors to my passed and failed port. I can click on my prompt and run. It allows me to choose my file geodatabase and then choose the grid that I want. K28 should now come through the passed port. Everything else should go through failed. So this should be K28. Tile name K28, and everything else is not K28. With the examples that we've been using so far, we have actually been dropping down a lot of transformers and only running the translation at the end. That's really because of the time constraints of the course that we're going through. In practice, whenever you add a couple of transformers, you should run a test translation. That way, if things are not going as you expected, you have a limited number of transformers to troubleshoot. I try to run the translation after pretty much every transformer I put down. Okay, so now we want to query our file geodatabase based on these grids. To do that, we'll be adding a feature reader. Feature reader transformer on our past port. So within the feature reader, we indicate the data set we want to query, city data. We're only interested in one table, so under the parameters, table list, I'm going to change this to not be city grid. I want to find all the address points. So you can specify what type or what feature types you actually want to query. I specified the feature type on the previous panel. I want the address points. We can narrow down which ones we want by adding a where clause, but in our case we want all of the address points. And we're going to select based on a spatial relationship. So any of the address points which are contained by the city grid will pass this test. Coming out of this, we want the resulting attributes and the resulting geometry only. Basically, we want coming out of this the address points. So let's right-click on this, connect inspectors, and see what we have coming out. Actually, let me stop that. Let's select an area, say L24 in this case. When I just hit run, it would use what I had for the previous translation run, so it should only be selecting one grid still. There we go. So we read in 30 grids. One of them, the one that we're interested in, passed our test. Coming out of that, we got 163 address points. The initiator output port passes out our grid, so we can visualize that as well. So in the universal viewer, we can see our grid, in this case our L24 grid. And these are all the address points within that particular grid. Okay, it's 10:30. Let's take another 10-minute break.